let's talk about solutions or solution formation. Now, a solution is simply what we learned in Chem 1 was a homogeneous mixture. That's all it is. And what do we mean by homogeneous? We mean that it's uniform throughout the bulk of the mixture. So uniform concentration would be another way to say that. And you make homogeneous mixtures all the time. If you put some sugar in your coffee, sugar in your tea, if you just make coffee, that's typically going to be a homogeneous mixture. So here's your cup of coffee, cup of joe, and it's got here, and you've got caffeine and some color that are uniformly distributed throughout the solvent water. And water's the solvent simply because it's in greatest amount. So you have two components. You have the solute, and that's just the component of your solution or your homogeneous mixture that's in lesser amounts. And then you have the solvent, and the solvent is in greater amount. And typically the solvent that we will be using in this course is going to be water. That is almost always going to be our solvent, but we will talk about some other types of mixtures that use different solvents. So here's sodium chloride, and sodium chloride, as you might remember, if I have a container here and my container is full of good old H2O and I put some sodium chloride into the H2O, it's a strong electrolyte, which means that it completely dissociates into sodium cations, chloride anions. So we'll have chloride anions, sodium cations, and the concentration over on this part of the solution will be the same as the concentration on this side of the solution. Now, what we just studied, intermolecular forces, has a great deal to do with this. Water, if water's our solvent, it's a polar molecule. All ionic compounds are polar, and many of those ionic compounds will dissolve, and this is the way they dissolve. Since sodium cation has a positive charge, you're going to have the polar water molecule orienting itself to the sodium cation with the oxygen ends pointed at the sodium cation. And the reason for that is oxygen is more electronegative. It has a partial negative charge, and you know how this works. Negative and positive charges are attractive with respect to each other. Since this is an ion, a cation, and this is a polar water molecule which has a dipole moment, okay, that's what we say about polar molecules. They have a dipole moment. We would call this ion dipole effect. That's the intermolecular force that's allowing the polar water molecule and the sodium cation to be attracted to each other and for them to form this homogeneous mixture, which we call a solution. All right. Solutions are just homogeneous mixtures. Water's the solvent, present in greatest proportion. Sodium chloride, those would be the solutes. We've got other kinds of solutions like grain alcohol. That's just ethanol dissolved in water. Takes me back to my high school days. Don't do that. It's really hard on your brain. I might have been somebody if I hadn't done so much of that and other things. So up to 100 proof or a good scotch and soda or even a beer. Speaking of beer, beer has naturally forming carbon dioxide in it, and it is dissolved uniformly throughout the water in the beer. And so that would be, as long as it's dissolved carbon dioxide, not bubbles that are emerging, that would be considered a homogeneous solution as well. So carbonated water. Air is a gaseous solution made up of nitrogen, oxygen, carbon dioxide, some trace gases. And in this particular case, the nitrogen is about 78% of this solution. Oxygen's about 21%. and carbon dioxide's 0.03%, and then you can just add in a little bit of methane, hydrogen sulfide, because human beings, cows, we all expel some pretty rank gases, to be honest, as a part of our metabolic function. But at any rate, in this particular case, nitrogen would be the solvent because it's simply in greatest amount. That's our simple definition. You can also have solid solutions like brass, which is just zinc in copper. And here are some other solid solutions like steel, 98.5% iron, about 1.5% carbon. If you get too far, go too far with the carbon, you've got cast iron, and it gets brittle, but it's quite strong. Sterling silver, white gold. Why white gold? I don't get it. And then silver about 4%, gold about 75%, and then you can have other metals like palladium and copper. All right, so predicting the solubility of a substance. The solubility is just the measure of the amount of solute that can be dissolved in a particular solvent. Ignore the chapter reference here, but do go back and study molarity, because we're going to get to concentration units here very shortly, and you remember molarity, it's equal to moles of solute, okay, solute, divided by liters of solution. You take the whole volume of the solution in liters, you divide moles of your solute into that liters of solution, and that gives you the most common unit of concentration we use, which is molarity. Now, here's the deal. Not every solute is going to dissolve in every solvent. The more alike that the solute and solvent are with respect to their polarity, the more likely they are to be soluble with each other. So polar solutes will tend to dissolve in polar solvents, and nonpolar solutes will tend to dissolve in nonpolar solvents. So solubility is driven by thermodynamics. Okay, thermodynamics, just the movement or the change, the exchange of heat throughout any particular process. By the way, insoluble means not soluble. And so what we call insoluble typically has a limit. It doesn't mean it's 100% insoluble, but if it's 0.01 moles per liter, if that's the limit of solubility for a solute-solvent combination, we call it an insoluble compound in a particular solvent. All right, enthalpy in solution formation. Again, let's ignore the chapter 5 reference. That was for a different book, but this video is in the right place in your particular course. So recall that delta H is the change in enthalpy, or change in heat under conditions of constant pressure, and the energy associated with bond formation. Okay, so example, water molecules, in order for them to be converted from a liquid to a gas, they have to separate from each other. Okay, they start out, if you're in a liquid phase, they're sloshing around each other, they're making and breaking what we call hydrogen bonds, you know about those, and as you stir them up and you get them going faster and faster, eventually what happens is they get separated further and further apart, so far apart, in fact, that that hydrogen bond between the water molecules breaks and they move into the gas phase. That is a thermodynamic effect. It's endothermic. You're putting energy into the system, and it has a delta H of 44 kilojoules per mole positive values. That means 44 kilojoules are required to separate a mole of water molecules, move them from the liquid to the gas phase, to vaporize them. What is the change in heat in kilojoules per mole of water? Is the process endothermic or exothermic? Well, from liquid to a gas, that's going to be endothermic. From gas to a liquid, we call that condensation. That will be exothermic. Okay? All right, so this is simply a diagram of the enthalpy of solution formation. You've got, let's say, a solute that's solid. And in order to make room for the solvent particles, you have to add enough energy to separate those solute particles from each other. And you can see in this diagram that these guys right here, they're now further apart from each other than they were in the previous phase. We'll just call this a solid because that looks like a solid. Okay, here's our solvent particles. They're also close together. It's less organized, so that's indicative of representation of a liquid. And so in order to mix these two, not only do we have to separate the solute particles from each other, we also have to separate the solvent particles from each other to make room so that these solute particles can get in between all of these solvent particles. And in order to do that, we have to put energy into both of these systems. So on the front end of solution formation are two endothermic processes. That means we're going to have a positive delta H here, a positive delta H here. Now, here's where the energy payoff goes, because most solutions most spontaneous processes, if something happens, most of them are overall exothermic. That means that energy gets released, and this is indeed an exothermic process. So this is exothermic. That means that energy is released, and we'll call it in the form of heat. And this is energy. This is basically you're having to add heat here. So you're adding heat or energy to make this work. And in this case, heat is being released. So, and that's because you're forming new bonds. So breaking bonds requires energy, and forming bonds releases energy. And that's why stuff happens. That's why molecules form, because energy gets released. You're going down the energy hill. So if I want to know whether or not a reaction or solution formation is overall exothermic or overall endothermic, that is, I have a beaker or a cup, and it's got my solvent in it, and here comes my solute. Okay, I'm going to have two components to that. I'm going to have separating the solvent particles, that's a positive delta H. I'm going to have separating the solvent particles, that's a positive delta H. And then when the solute and solvent particles get together and form new bonds, that's going to be a negative delta H. That's exothermic. That means that heat is being released. Okay, it's leaving that system. Now, if I add up those two positives on the front end with the negative heat release, that's going to be a net exothermic process because the amount of heat released exceeds the amount of heat that is absorbed. And it's going to be exactly the opposite for a net endothermic solution process. It requires heat to break up solute and solvent particles, but the heat that's released, so when heat is released, when the solute and solvent particles get together, and I add up the amount of heat release, the negative delta H to the two front-end positive delta H's, if that winds up being a net positive, that's going to be a net endothermic process because these two values, their sum of these two values was greater than the amount of heat released. Hopefully that makes sense. So this would be net endothermic, where the sum of the front end, the solute solvent particles and breaking up, is greater than the amount of heat that gets released. This would be a net exothermic process because the sum of the amount of heat required to break up solute and solvent is less than the amount of heat that's released from solute, solvent, interactions, bond formation.